Welcome back, and welcome somewhere new. In the painter's studio, we learned to see pictures, but a picture holds a single moment, frozen. Rivers are different. Rivers hold time. This is the river house. The water below carries the days past our window, one after another, in order. And today, we'll teach a machine to do something quietly remarkable. To remember, our project, reading 60 days of a stock's closing prices, and gently sketching what tomorrow might look like. Take a breath. Listen to the water. Let's begin. Look at one leaf on the water. One price, $151. By itself, it tells us almost nothing. Is the price rising, falling, resting? We can't say. Now watch the whole procession, day after day, in order, and suddenly there's a story, a gentle climb, a small stumble, a recovery. This is time series data. The values matter, but the order matters just as much. Every dataset we've met so far could be shuffled like a deck of cards. Not this one. Shuffle a river, and it stops being a river. So today we need a new kind of model. One that reads the days the way you read a sentence, left to right, remembering what came before. Every river house keeps a logbook. Ours is called AAPL.CSV, roughly 10 years of Apple's trading days. Watch each line run. First, Pandas arrives, our patient librarian, then reacts, and the logbook opens. 6 columns. The date, the opening price, the day's high and low, the closing price, and the volume. How many shares changed hands. We convert the dates into real calendar dates. And then, very important, we sort. Time series must stay in order. Always. 2,516 days. That's our river. Let's walk through this together, line by line. First, we import Pandas as PD, our tool for reading tables. Then df equals pd.readCSV, opening the file called aapl.csv, and 10 years of prices settle into a table named df. Next, we take the date column, and pass it through pd.toDateTime. So Pandas treats each entry as a real calendar date, not just text. Then df.sort values on date, putting every row in true chronological order. Finally, printdf.head shows the first 5 rows, and printdf.shape tells us the size. 2,516 rows, 6 columns. Our logbook is open. Before we model anything, we look. Watch the line paint itself. 10 years of closing prices, flowing like the river outside. Notice the shape. Long, patient climbs, small daily wobbles, one deep dip, and a recovery. For this episode, we'll focus on just one column, the closing price, the last price of each day, the note the river leaves on our doorstep every evening. Take a moment here. This single blue line is what we're going to teach a machine to read. Let's read these lines gently, one at a time. We begin by importing Matplotlib.pyplot as PLT, our painting kit, then PLT.figure with fig size 12 by 5, laying out a wide sheet of paper, 12 units across and 5 tall. Next, PLT.plot draws the picture, taking df date for the horizontal axis, df close for the vertical, in a soft steel blue color. Then 3 small labels. PLT.title names the chart AAPL closing price. 10 years. PLT.label writes date along the bottom, and PLT.label writes price in dollars up the side. Finally, PLT.show, and the finished chart appears. 10 years of closing prices, in one quiet blue line. Neural networks are gentle creatures. They learn best when numbers are small, and close together. Dollar prices run from 77, up past 190, too wide. So we bring everything onto the river gauge. A scale from 0 to 1. Watch the ribbon. The lowest price becomes 0. The highest becomes 1. Everything else settles in between. And notice, the shape doesn't change at all. Only the size. One more thing, and it matters. We keep the scalar. Later, when the model whispers its answer in gauge language, 0.62, the scalar will translate it back into dollars for us. Follow along with me, slowly. First, from sklern.preprocessing, we import min-max scalar, then close prices. We take df close, pull out its values, and reshape with -1, 1, turning the column into the tall, single column shape the scalar expects. Next, we create the scalar, min-max scalar with feature range 0 to 1, then the gentle magic, scaled prices equals scalar.fit transform of close prices. Fit learns the lowest and highest price, Transform squeezes every value between 0 and 1. Finally, print scaled prices. First 3, and we see tiny numbers. 0.014, 0.000, 0.003. Same river, smaller gauge. Here is the most important craft of this episode, making sequences. A time series model learns from little stories. Ours will be 60 days long. Watch the net. It gathers days 1 through 60, and the answer it must learn is day 61. Then the boat rows forward. Just one day. Days 2 through 61. Answer. Day 62. And again. Days 3 through 62. Answer. 63. 60 days in. 1 day out. Over and over. All the way down the river. 2,456 little stories. The reshape at the end is just packaging. Samples. Time steps. Features. The shape Keras expects. And notice how we split for testing. No shuffling. The first years for learning. The most recent for the exam. We never let the model peek at the future. Let's take this one step at a time. First, import NumPy as NP. Then sequential length equals 60. Our window size. X and Y begin as two empty lists. Now the loop. For I in range. From sequential length to the length of scaled prices. Each turn. X.append takes the slice from I minus sequential length up to I. 60 days in. And Y.append takes scaled prices at I. Day 61. The answer. After the loop. NP.array turns both lists into arrays. Then the reshape. Samples. Time steps. One feature. Giving 2,456. 60. 1. Finally the split. The first 80% becomes train and itrain. The last 20% becomes test and itest. Time kept in order. Meet a kind visitor, who remembers only today. Each leaf delights him. Each price fascinates him. And the moment it drifts past, it's gone. The early stones wash away. Ask him what tomorrow holds. And he can only shrug. He knows today. Nothing else. This is an ordinary dense network. It's wonderful with pictures and tables. But hand it a sequence. And it sees a bag of numbers. Not a story. First day. Last day. All the same to it. To read a river, we need memory. That's all right. It's exactly what we build next. A recurrent neural network, an RNN, is a rope of hands. Each hand reads one day, writes what it learned on a note, and passes the note downstream, along with the day itself. Memory. Traveling with time. A lovely idea. But watch the ink. 5 hands in. Still dark. 15 hands lighter. 30. A whisper. By hand 50. The page is nearly blank. Every pass multiplies the message by a small number, and small numbers, multiplied again and again, fade toward nothing. This is called the vanishing gradient, and it means a plain RNN forgets what happened 60 days ago. Our windows are 60 days long. We need ink that lasts. So the river people built something better, a keepsake box. This is an LSTM cell, long short-term memory. Think of it as a keepsake box with a stream running through it. The stream is the cell state, the long memory. Stones placed in this water can travel a very long way, without fading. That's the whole secret. And around the stream, 4 little doors. The forget door asks what old memory no longer helps? Those stones are returned to the river, gently, without regret. The candidate shelf holds what today has to offer. New stones, freshly gathered from today's prize. The input door decides how many of those new stones actually enter the stream, and the output door decides what the box shares with the next moment. Not everything, just what's useful right now. 4 doors. Keep, offer, admit, share. If it feels new, that's all right, because next, we're going to watch it happen with real numbers, slowly. Let's slow everything down, and pass 3 real days through one cell. You can check every number. Monday arrives. The stream holds an old memory of 0.20. First, the forget door. Today it opens halfway. The forget gate is 0.5. Half the old memory returns to the river. 0.20 times 0.5. 0.10 remains. Now the candidate shelf offers what Monday brought, plus 0.40. The input door opens halfway too, so half of that enters, plus 0.20. The stream settles. 0.10 plus 0.20. The new cell state is 0.30, and the output door shares a soft note downstream. about 0.2. Tuesday arrives. A stronger rise. This time the forget door barely opens. 0.9. Because the recent memory is worth keeping. 0.27 stays. The input door welcomes more of today. Plus 0.28. New cell state. 0.55. Feel that? The memory grew. Because the trend grew. Wednesday brings a small dip. The forget door releases a little more. 0.33 stays. A modest new stone enters. Plus 0.15. New cell state. 0.48. The memory eased down. Gently. Just like the price did. 0.30. 0.55. 0.48. The box is breathing with the river. Now, the doors themselves are learned. At first, they open at all the wrong times. And the guesses are poor. Look at the wall chart. Epoch 1. The loss is 0.42. By Epoch 5. 0.18. Epoch 10. 0.08. 15. 0.03. And by Epoch 20. 0.01. Each epoch, every door's hinge is adjusted, a whisper at a time, until keeping and forgetting both happen exactly when they should. If any of this felt quick, that's alright. We'll watch the real training in a moment. Slowly, read these numbers with me. Gently. On day 1, Monday's value 0.52 arrives. The old cell state is 0.20. The forget gate is 0.5. So we keep 0.10. The candidate offers plus 0.40. The input gate of 0.5 admits 0.20. The new cell state is 0.30. The output gate of 0.7 passes about 0.2. On day 2, the forget gate rises to 0.9, keeping 0.27, adding 0.28. New state 0.55. Day 3 keeps 0.33, adds 0.15, settling at 0.48. And below, the loss falls from 0.42 down to 0.01. Now we build, and it's smaller than you might expect. Watch the lines run. Sequential, a channel for the story to flow through, one layer after another. LSTM, 50. 50 keeps 8 boxes, side by side, each one reading the same 60 days, each learning to notice something different. One may care about slow trends, another about sudden dips. The input shape, 60 time steps. One feature, tells them what a story looks like. Dense. 1. A single gold pencil at the end, that takes everything the boxes remember, and writes one number. Tomorrow. Then compile. Adam is our patient caretaker, adjusting the hinges. Mean squared error is the measuring bowl. It catches how wrong each guess is, and cares most about the big misses. 2 layers. That's the whole model. Sometimes the quietest tools are enough. Let's build it together, line by line. First, 2 imports. Sequential from TensorFlow Keras models, and LSTM and dense from TensorFlow Keras layers. Then model equals sequential, a simple stack of layers. Inside, the first layer, LSTM with 50 units, and input shape 60,1. 50 memory cells, each reading 60 days of a single feature. The second layer, dense with 1 unit, a single output number, tomorrow's price. Next, model.compile. The optimizer is Adam, our patient adjuster, and the loss is mean squared error, which measures each miss and cares most about the big ones. Finally, model.summary prints the receipt, every layer listed, with about 10,000 parameters ready to learn. And now, we let it learn. 20 epochs, 20 patient journeys through every story in the logbook, 32 stories at a time. Watch the rhythm. A story flows through the boxes, the pencil guesses, the bowl measures the miss, and the caretaker adjusts every hinge. Just a whisper. Epoch 1. The loss is 0.42. The doors barely know when to open. Epoch 5. 0.18. Epoch 10. 0.08. The guesses are finding the river's rhythm. Epoch 15. 0.03. And Epoch 20. 0.01. Notice the terracotta thread too. The validation loss, measured on days the model has never seen. It falls alongside. That's the sign we want. Real learning, not memorizing. Rest here a moment. The boxes have learned when to keep, and when to let go. Follow the training call with me. We write history equals model.fit, and hand it 5 gentle instructions. First, strain and itrain, the stories and their answers. Then epochs equals 20. 20 full passes through the training data. Batch size equals 32. The model learns from 32 sequences at a time. Validation data is test, test. So after every epoch, it is checked on days it has never seen. And verbose equals 1. So we can watch. Below, the story unfolds epoch 1, loss 0.42, epoch 10, 0.08, and by epoch 20, loss 0.01, with the validation loss close beside it at 0.013. Learning, not memorizing. Now for the moment we came for. We gather the 60 most recent days, the freshest water, and pass them through the model one last time. The boxes read the story, the doors keep what matters, and the gold pencil sketches 1 point, just past today's edge, 0.62. Engage language. Our faithful scaler translates it back, $187.42. But look at the mist. That soft band around the point is the truth about forecasting. The model isn't certain. It's saying somewhere near here, roughly between 184 and 191. And let's say this plainly, while the light is golden, a forecast is an educated guess, never a promise. Markets are moved by news, moods, and moments no model has seen. We learn this craft to understand patterns, not to gamble on them. The mist isn't a flaw. The mist is honesty. Let's read the forecast code, slowly. First, last 60, we take scaled prices from -60 to the end, the most recent 60 days, and reshape them to 1,60,1, a single story for the model. Then tomorrow scaled equals model.predict of last 60. The boxes read the story, and out comes one number. Engage language, about 0.62. Next, tomorrow price equals scalar.inverse transform of tomorrow scaled. Our faithful scalar translates it back into dollars. Finally, the print line formats it to 2 decimal places. Tomorrow's predicted close, $187.42. 4 small lines, 1 gentle glimpse of tomorrow. How well did we really do? We ask the days the model never saw. Watch the 2 ribbons. Steel blue, the truth. Terracotta, the model's guesses. See how closely they braid. 3 gentle instruments give us numbers. Mean absolute error. On an average day, our guess misses by about $2.14. RMSE, root mean squared error, a stricter cousin. It presses harder on the biggest misses. $2.87. And the miss is a percentage. 1.42%. For every $100 of price, we're off by about $1.50. Remember the mist, though. These ribbons braid beautifully on quiet waters. It's the sudden storms no model sees coming. Walk with me through the checking. First, from Sklern metrics we import mean absolute error and mean squared error. Then predict at scaled equals model.predict on's test. Guesses for every unseen day. 2 translations follow. Scalar.inverse transform turns those guesses into predicted prices. And it reshaped, becomes actual prices in dollars. Now the 3 measurements. The mean absolute error of actual versus predicted. $2.14. RMSE, the square root of the mean squared error. $2.87. And the average absolute difference divided by the actual price, times 100, 1.42%. Finally, Matplotlib plots both lines, actual in steel blue, predicted in dark salmon, so we can watch the 2 ribbons braid. Let's set our 2 travelers side by side. Kindly, the RNN passes a note, hand to hand, simple, light, and for short journeys. Honestly, it's fine, but its memory fades. Over 60 days, the ink pales to nothing. The vanishing gradient we watched on the riverbank. The LSTM carries a keepsake box. The cell state flows through it like a protected stream. And the 4 doors. Forget, input, candidate, output, decide. At every step, what stays and what goes. The cost? More parameters, roughly 4 times more. Doors are not free, but for long stories, 60 days of prices, a paragraph of speech, a season of weather, the box wins, gently and clearly. That's why we chose it. All that learning, every hinge, every door, now lives in one small box. 1 line saves it. Model save, stock_LSTM.keras. We wrap it in cream paper, tie the ribbon, and shelve it. Tomorrow, or next year, 1 line brings it back, exactly as it is now, and a small kindness to your future self. Save the scalar too. The model speaks engage language, 0 to 1. Without the scalar, no one can translate its answers back into dollars. 2 parcels on the shelf. the box, and its gauge. One last walk through the code, short and sweet. First, model.save with the name stock_LSTM.keras, and everything the model learned, every weight, every gate, is written into one small file. Later, anywhere, 2 lines bring it back. From TensorFlow keras models import load model, then model equals load model of stock LSTM.keras, whole again, exactly as trained. And one kindness more, import joblib, then joblib.dump saves our scalar into price_scalar.pkl. Remember, the model speaks in gauge language, 0 to 1. Keep the scalar beside it, so its answers can always come home to dollars. Wherever time flows, this craft is at work. Weather stations read weeks of sky to sketch tomorrow's rain. Power grids read the evening's rhythm, so the lights never flicker. Your phone's ear, the one that turns your voice into text, reads sound as a sequence, one moment leaning on the last. And in quiet workshops, sensors listen to old machines breathe, and whisper service soon before anything breaks. Different rivers, same keepsake box. What you built today is the real thing. Our river reads time one day at a time patiently, in order. But listen across the water, in that glass aviary, every songbird can look at every other bird, all at once. No waiting, no passing notes, just sunbeams of attention, connecting everything to everything. That is the transformer, the idea behind the language models changing our world. It's our final door, and the most beautiful one. Rest here a moment, by the water. When you're ready, the next door is open. You taught a machine to remember. That's no small thing. Sleep well, little river. See you at the aviary.